Now let's move to our second part. It's adversarial training. Let's train a robust model. So it happens in the training part here. This is a training part. We want to train a robust model in adversarial training, in adversarial defense. So there are three pipelines. I mean, the main difference, three pipelines. The first is just the basic adversarial training. It will generate adversarial examples. You can say this step, this step is generate adversarial examples, okay? And then we will train the model with adversarial examples. So it's like the min-max theory. So first we will find the adversarial examples. Means that we want to find noise such that this for this some example, its loss value will reach its maximum. Okay, and then we will train the model with this kind of adversarial examples. Okay, yeah, that's a basic one. It's called adversarial training. Another two is called instance-related adversarial training. It will reweight each instance. The last one is pixel-related adversarial training. So it will focus on the image level. We want to reweight each pixel. Okay. So in the first pipeline, adversarial training, except for the basic adversarial training method, it's like we want to train the model with the adversarial examples. In the trace, the authors also found this theoretical bound, and they found that we need to consider trade-off between adversarial robustness and accuracy. Okay, so here we can look at the loss function here. It's a nature error plus robust error. Okay, a nature error encourages nature error to be optimized by minimizing risk with ground truth label. Robust error encourages the output to be smooth in combating adversarial attacks. Okay. And after that, researchers found that for different samples, okay, it might need different focus. Okay. Especially for samples misclassified. Okay. So they propose misclassification where adversarial training. So here, they have three terms in the method. First term, I commonly use a CE loss or cross-entropy loss with a margin term to improve decision margin. The term two is to measure if model prediction are consistent before and after adversary perturbing. Okay, so we want the prediction before and after adversary perturbing, can be maintained. Okay. And term three, and we want to emphasize the learning on misclassified examples. Okay, so if it is misclassified, we want to ensure it can have more weights to be considered. Okay. Okay, the next one is called instant-related adversarial training. In this method, we will directly work on the adversarial training method, but we will provide different weight for different different samples. Okay, for different samples. So it's first work in this field. It's called a Garrett. It's geometry aware instance-related adversarial training. The main idea is that the data point close to the class boundary is less robust, requiring larger weight in training. Okay. So how could we measure if data point closer to class boundary or not? And they propose a list PGD steps called LPS. Okay. So what is that? We can look at this figure on the right side. We often have nature examples, okay? And we will attack these nature examples by PGD. It's a attacking method. This method always have some steps to finally such that the loss function on this nature example is large enough. Okay. So we can look at the first step, second, third, four, five, six. We can find that at step 6, the nature example is past the descent boundary. It means that we successfully attack nature example to be far away from its original ground truth label. Okay, so here we call 6 as LPS, the least PGD steps. Okay, as LPS. Okay, and based on this LPS, we can just design a weighting function. okay, and to give a different weight to the adversary examples, okay. Specifically, if we found that data point closer to the class boundary, okay, we will give the larger weights in training. However, we found in this kind of method, we found that it has two major problems. The first problem is this kind of method is path dependency. Okay, so it may change given the same start and end point. Yeah. So now if we consider the adversary variant is here, nature example is here. We can sometimes we just need to slightly change the attacking method, and the path will change. The path will change. It might start uh, before it cross the descent boundary. Okay, for example, it 5 might be 10 or 11. Yeah, sometimes. Yeah, so it means that this kind of method is not stable. It's not stable, right? Because for the same adversary data and same nature data, LPS might change, so it's not good property. The other thing is discreteness. You can say for this step value, okay, it's always integer and it can only take the field value, for example, 10 or 12 or 50, okay. And it will make the measurement ambiguous, okay, ambiguous, not precise. So the first one is path dependency. We can say we just need to change PDD to other things, and it will change the loss curve a lot. And for discreteness, we can say for LPS is being equal to 10. Okay, we have many fail case here. Okay, it's not what we want. It's the information here is highly mixed. We cannot use that information. And it will cause the consequence. If we look at this figure, we can find that for Garrett, okay, although its PDD is good, its PDD performance is good, but its CW performance is drop a lot, right? It's drop a lot, yeah. So it means that this both issues will cause a previous Garrett fail when we make different attacks. So how to solve that? How to solve that? In this work, we consider a more direct way, like remember what's the idea in the instance related adversary training is that we want to measure if this data close to descent boundary or not. Okay, why should we not just do it? Just measure the distance between the point and the descent boundary. Okay, so here we bring the idea for multi-class margin in margin theory, and we also compute in a low dimension embedding space with normalization. Okay, so this is our probabilistic margin. Okay, probabilistic margin. For example, if this y is a ground truth label, this value, if it is predict correctly, this value might close to 1. Okay, and this value is just the others. Okay, except for y, except for ground truth y. So ideally, if this is 1, this will be 0. Okay, for all other things, it will be 0. If this is sorry, if this one, if this one is yeah, if this one is 0.6, and perhaps the second largest one might be 0.2 or 0.4. Okay, so this margin will be, yeah, 0.4, 0.2. Okay. When we consider this probabilistic margin, we know that the positive margin means that it's safe data with correct prediction. Okay. Because the ground truth label, the probability corresponding to ground truth label, okay, is always the largest one. Okay, so this py is always the largest one among all logits. So positive value means that safe data with correct prediction. Zero value means that it's safe data on descent boundary. Okay, on descent boundary. And negative value means that critical data with wrong prediction. Okay, So we can look at these three description. We know we can just use this probabilistic margin, this value, okay, to help us identify it's closer to decision boundary or far away, okay, and propose mining. So we can design mining probabilistic margin, and for each margin we can just give the a weighting function based on this margin, okay, and try to get the result, okay. Okay, the last one pipeline is called pixel-weighted adversarial training. Okay. So in this work, it's like very recent work. It's SML 2024. In this work, we found that if we change the perturbation budget in different region, okay, the adversarial performance, adversarial robustness, and nature accuracy will change a lot. For example, in this case, if we consider setup one is okay, for bottom right, we give the perturbation budget of 6 over 255, okay? And for setup two, we give the upper left 6 over 255, okay? You can see the overall perturbation budget is the same, okay? But we found that for the for the second setup, okay, the nature accuracy is larger and the robust accuracy is larger. Okay. It means that when we change perturbation budget among different pixels, it might change the adversarial loss and it might change adversarial accuracy and the nature accuracy a lot. Okay. So it motivates us to consider, okay, can we give different perturbation budget to different pixels? Okay, to different pixels. So that's the main idea. Another thing, okay, now we're considering different pixels. Okay, so the main thinking is that which pixel should be given more perturbation budget and which should be given less. Okay, how to decide important or non-important area in the pixel region? And here we consider to use class activation mapping, and we will give original perturbation budget to the important area and slightly lower the perturbation budget for non-important area. Okay. And that's the main pipeline for part pixel-related adversarial training. Okay. Yeah, we can look at that here. We will, after some warm-up, we will get the feature map and we will get class activation map. Based on this map, we will generate a mask. So for important area, the perturbation budget will be set to original one, for example, 8 over 255. And for the remaining part, we will set it to 7 over 255. Okay, we cannot reduce it to 0. It doesn't make sense, but we can slightly lower the perturbation budget. Okay. And then we just Wells product with the perturbation we learned. We got new adversarial images and we fit it to the training precise and minimize the training loss on this kind of adversarial images. Okay. So what's the main drawback? What's the main advantage for this kind of part? For the part, okay. The main advantage is that because we slightly lower perturbation budget for some area, okay, so overall perturbation budget is actually lower. It means that we will get a very nice nature accuracy, okay, very nice nature accuracy, okay. So in the experiment, we also found that for this kind of method part, the trade-off between adversarial robustness and the nature accuracy is improved a lot. Specifically, nature accuracy will be improved a lot, and for adversarial robustness, it will be maintained or slightly improved. Okay. Yeah, so that's the main idea for this pixel-related adversarial training and why it can work and why it can help us improve the nature accuracy.